friends, welcome to second lecture on chemical vapor deposition. During part 1 we have covered the introduction about CVD, then construction of CVD system, and we have started types of CVD system in detail. So remaining types we will cover in this part 2. Okay, so begin with next, that is photo enhanced CVD, or maybe in short we are calling it is PHCVD process. So based on activations of the reactants in the gas or vapor phase by electromagnetic radiations, short wave, ultraviolet radiations, generally we are using a selective absorptions of photonic energy by the reactant molecules or atoms initiate the process, and low temperature, generally 150 degrees centigrade, needed to form films like silicon dioxide, greatly minimize the radiation damage. So here you can see that we are using certain kind of UV lamp chamber from where we are generating the UV source. Okay, so here you can see here. Then UV source, it is coming UV, which eliminates UV lights, and then we are plunging some kind of carrier gas, then that carrier gas is reacting with the UV rays, and then they are forming certain kind of material, then that material is going to deposit onto the substrate itself. Okay, let us discuss the next one, that is a laser induced CVD. So it allows local deposition of material within the focus of the laser. It allows in first step deposition of the structures with the lateral dimension down to at least 1 micrometer. 3-dimensional substrate of micro size is possible also. So from this particular type, as I have shown in the figure also, you can understand that we have given us an example of CNT, okay, carbon nanotube. Okay. So any kind of laser source you can take over there, and then the laser source you have to put in, then and there is having some many inlet channel where you are plunging the carrier gas, where you are plunging different gas with which we can react properly, and then through these laser these gases will agitate it, and they will form certain kind of material, new material, in which will be deposited onto the that carbon nanotube. Okay, now let us go for the next, direct liquid injection CVD. Okay, so here precursors are in liquid form, liquid or solid dissolved in a convenient solvent liquid solutions are ejected in a vaporization chambers toward the injectors, typically like a car injector. Then a precursors vapors are transported to the subtracting classical CVD process. And the simple thing is that car injector is nothing but that when the fuel is directly coming and it is injected into the engine itself, so we are using certain kind of injector over there, so that is continuously injecting that of oil and air mixture, and continuously the burning takes place. The same things we are doing over here also. So we are having some kind of pressure precursor tanks where we are putting certain kind of gas pressure. So due to that gas pressure is taking place, and directly the liquid, it is going into the atomization process, or maybe generally we are calling atomizer. So where this liquid is going, then a high pressure of air we are giving, due to that liquid is forming small bubbles, and then that small bubbles is directly coming as a vapor, and then it is deposited onto a metal surface, and the rest of vapor it is going throughout the chamber. Okay, now let us discuss the next one, metal organic chemical vapor deposition. Okay, so based on metal organic precursors used to produce single or polycrystalline thin flames, high complex process for growing crystalline layers, pressure is generally 10 to 760 torr, and this technique is preferred for thermodynamically metastable alloys. So here generally we are using certain kind of metal precursors over there, and then we need a high energy source over there. Then the materials we are going to deposit is this, as I have shown in the figure also. Here only metal ions will stick with the substrate itself. Okay, now let us go for the next one, latest technology, that is a CVI. Okay, chemical vapor infiltration. This is latest technology. Now CVI means the chemical vapor infiltration is a ceramic engineering process whereby matrix material is infiltrated into the fibers, which performs by the use of reactive gases at elevated temperature to form a fiber reinforced composite. So not only that, you can make the composite over there. So here you cannot do the coating of particular material, you can do the coating of particular composites too. Here this CVI was the infiltration of the fibrous alumina with chromium carbide. CVI can be applied to production of the carbon composite and ceramic matrix composite. A similar technique is the chemical vapor deposition process. The main difference between deposition process of CVD and CVI is in CVD process hot bulk surface is not there, while the in CVI deposition process porous substrate is used. So that is a basic difference. From this particular case, you can understand that inlet we are putting the chemical carrier gas and the reactant material over there. Then carrier gas is going through this fibrous material, and then that molecules is reacting inside, and some molecules with the carrier gas is going out of material. That means the carrier gas it can easily go inside the porous material, and then the molecules of that particular reactant material can be absorbed inside the port itself. Some molecules may be come out with the carrier gas. So by this way we can do the CVI process, chemical vapor infiltration. So here we are doing the infiltration of particular molecules inside the material. Now next, hybrid physical CVD process. So vapor deposition process that involve both chemical deposition of precursor gas and vaporization of solid source. Main difference between the HPCVD and other CVD means it is in heating unit, both substrate and solid metal source, and heated up by the heating molecule. Okay, so this is about this hybrid physical CVD. Now next one is the rapid thermal CVD process. This one, so use of heating lamps or other method to rapidly heat the vapor substrate, heating only the substrate rather than the gas. So chamber walls helps reduce the unwanted gas phase reaction, and that can lead to the particle formation. So still now we just are agitating those react material and those gas material. But in this particular case, just we are agitating our substrate so that it will make itself as a reactive, so that it can react with the gases and then form any kind of layer or maybe the powder or maybe the coating onto the it. Okay, now let us go for the next, that is a plasma enhanced CVD process. This is also latest technology, and that these equipment are very expensive too. So LPCVD with plasma source, ionized gas in plasma supplies energy to the reactant gas, and lower deposition temperature to 200 to 350 degrees Celsius we have to keep, and it is good for deposition on multi-layer film sensitive to temperature also. So this is all about plasma enhanced CVD process. Let us discuss the next one called high density plasma CVD. Plasma enhanced CVD with very high density plasma. Here the density of plasma is more, and then RF bias on substrate. Lower deposition temperature, generally 20 to 150 degree centigrade. Much lower pressure needed, generally 1 to 10 metal is required, and better quality films with less wires. So this is most sophisticated machines than the plasma enhanced process. Okay, The next one we are going to discuss about the combustion CVD or maybe the CCVD process. In this particular case, it is divided into 4 parts. So it is the ability to produce thin film in the open atmosphere using vapor precursors or maybe inexpensive precursor in chemical in solution. So generally, like a painting, we are using this kind of technique over there. First one is called solution preparation. This is first step, starting with precursor of materials are dissolved in a suitable aqueous or maybe the organic solvent. So here we are putting the solution over there. So this solution to pump, it is going in particular nanomizer or maybe that gun which is going to spread those material into the surface itself. Then in the meantime, we are using certain kind of filter. Maybe there is some impurities, there may be there certain kind of humidity, or maybe that there is a certain kind of water molecules that can be absorbed directly, so that the material, the solution in a dry form, it will go directly to the nanomizer. And here in this particular case, we are doing the atomization of that particular gas. What is that atomization or maybe atomizing gas? The solution is delivered by means of pump of to a proprietary atomizer where it is covered into submicron droplet. Here we are giving a high force of gases, so through these gases, these solutions in the liquid form is coming to the small bubble form and then directly towards through this film structure. Then it is giving certain kind of combustions of that particular junction, and then that film is directly falling onto the substrate and it is making the certain kind of coating over there. Okay, now we are going to discuss what are the considerable factors for selecting suitable CVD system. So first factor is reactant used in the process. Okay, so next one is the maximum acceptable leak rate for air into system. Third parameter factor is purity of the deposit, and then size and shape of the substrate, and last one is called process economy. That means why that the whole process is expensive or maybe it is cheap, and not only that, what type of substrate material you are going to use, why that reaction in between your reactive gases and substrate material can be done or not, what are the condition inside the chamber you require, whether you need a more pressure or less pressure, then whatever the energy source you are going to use, or maybe your material can sustain. So depending on all those things, you have to choose the better CVD mechanism for your particular substrate. Okay, now next, what are the advantages? So first is uniform distribution over large areas, then no compositional gradients across substrate, then no need to break vacuum for source changes, then more selective area deposition because of higher activation energy for a reaction with foreign substrates. CVD layer always follow the contour of the substrate, they are conformal to the substrate itself. So this is a technology, this is all about advantages of CVD process. Let us discuss the disadvantages. So first one is called the most involved safety and contamination. That is a big problem over there. It can contaminate with the source, it can contaminate with the material, it can contaminate the equipment. Then next is the hybrids and carbonyl are poisonous. Then next is the metal organic are pyrophoric, ignite in contact with air. Then high cost for compounds with sufficient purity. Then they are not possible for some materials, means they simply is no suitable chemical reaction, and they are generally not suitable for mixture of materials. So these are the some disadvantages. Let us discuss the last part of this CVD technique, that is the applications of CVD technique. Generally we are going to use for the microelectronics purpose, conductors, passivation layers, diffusion barriers, oxidation barriers, etc. Semiconductors, lasers, optical fibers for telecommunication. Then optical fibers are produced by coating the inside of the fused silica tube with oxides of silica. Then we are using for the solar energy purpose also. So solar energy conversion by the utilization of selective absorber and of thin film solar cells of silica and gallium arsenide and dye sensitized solar cells also. Then for carbon nanotubes for advanced electronics purpose, biological and chemical devices and detector also. Then where resistance coatings have wide industry application. So coatings of titanium carbide, titanium nitride and alumina on cemented carbon cutting tool insert of a titanium carbide or steel on steel. Okay. Then friction reducing coating, then corrosion resistant coating, erosion resistant coating, heat resistance coating. Again for high temperature superconductors for use in medical, power grid, high energy physical application. Then fibers for use in fiber reinforced materials. Then structural shape. Okay, again you can use for the decorative coatings. Okay, for example titanium nitrate, or you can say for the gold plating or gold coloring. Okay, on the watches. Again for the conductive coatings for integrated circuit, interconnects, display application, solar control, electrochromic windows, automotive windows. So for these all applications you can use chemical vapor deposition surface coating technique. Okay, so here I have given the some summary about this. Okay. So this is about our today's lecture. Okay, here we have finished the CVD technique. Thank you.
Hopefully you might have enjoyed the lecture. Then please do like the video and know your thoughts in comments. Please do share this video among your friends and don't forget to subscribe to our channel. After subscription you can press the bell icon to never miss the notification regarding our new videos. Thank you so much.